Okay, so welcome back, everybody. Hope you enjoyed your lunch. So we got two more parts coming up, and the number of slides are going to be less than in the first two ones, so you might be pleased to hear that. So I'm not going to go into many technical details, and maybe we can discuss a few things with questions as well. I don't want to, again, I just want to give you brief overviews of some of the techniques that have been developed. So the next part is advanced linkage technique. So specifically looking at more recent ways of how we can scale up record linkage by looking at scalable indexing and blocking techniques. And then a bit more about these collective techniques and learning, machine learning based techniques basically, which have shown to be quite successful in the last few years. And then the last part, we have another break, a coffee break, and then the last, I don't know if the coffee going to be there.
No fresh coffee.
Sorry, no fresh coffee, bad news. But there should be drinks out there maybe, hopefully so. I'm having a 5-minute break. And then the last part will be about privacy issues, which I think many of you are interested in as well. Okay, so let's have a look at recent indexing, or recent, maybe different or more advanced techniques of how we can scale things up. So the first one is what's called sorted neighborhood. It's actually not that recent, it's about 20 years old as well, but that has shown to be very successful in deduplication of business mailing lists. And the idea is very simple. We sort our database according to some of the attributes or columns we have, and then we have a sliding window of a certain size, and we compare the records within that window size. So as an example, let's assume we have this small database here, which it's not a database where we extracted first and last names of people. So Abby Bond, Paul Smith, Pedro Smith, etc., up to Sally Taylor. So we extract first and last name. We generate that sorting key, as we call it. These record numbers would just be the links back to the original database. We sort the database alphabetically according to these keys. And now we have, let's say the window size here is 5. So we basically grab the first 5 records, go back and grab the actual records and compare all the records within that window. So we compare our 5 with our 2, with our 4, our 9, our 1, our 2 with our 4, etc. Once we've done these comparisons, then we slide the window 1 position down. So now we remove Abby and we add Peter Smith. The only thing we have to do now is compare record 7 with the 4 records which are in the same window. So we compare our 7 with our 1, with our 9, with our 4, with our 2. Then we slide the window position down. We remove Paul Smith, and we add Peter Smith, so our 10, and we compare our 10 with the previous 4 records. So we slide that window all the way down until we have the last 5 records. The nice thing with this is that we can control the number of comparisons, because basically every record here will only be compared with the previous 4 records. So the computational complexity is not depending, we don't have different block sizes, and then we put all the Smith into one block and all the Dijkstra in another block. We're always going to have the same number of comparisons which we do. So we're going to compare basically, if the window size is W or X, then we always compare every record with the X previous or the X minus 1 previous records. So it gives us a linear complexity in the number of comparisons. The problem, of course, is again, if we have data quality issues, if we have Christine instead of with CH and Christine with a K, then they're not going to be sorted next to each other. So Christine might be up here, and Christine, well, in this example, actually going to be next to each other. If you find a different example. But in a large database, you can imagine a CH Christine is going to be far away from a K Christine. So we're not going to compare them, right? So that's why, similar like in blocking, we have different blocking keys. We need to have different ways of how we sort the database. So we might sort it on first name, last name, and do such a run. Then we might sort them according to the postcode or suburb. Then maybe based on last name or first name, last name, first name, and things like that. But this has shown to be very successful in many applications because it scales up much better compared to the traditional blocking, because we can really control the size of how many records which we're going to compare. And more recently, a few years back, there have been several techniques which calculate the similarities between these keys, and instead of having a fixed window size, they adaptively change the window size as well. So, for example, if Percy Smith is in the window and we see that Percy Smith and Alan Bond has a very low similarity, we don't grab the actual records because we know they're very likely going to be the same. So we can adjust the window size depending on the characteristics. So that's one way of how we can make things more scalable. Another approach which we developed about 10 years back is again based on these Q-grams. The aim of this was really to look at very dirty data where we have lots of typographical errors. And again, we convert strings into Q-grams, and now we insert every string or every record into several blocks. So for example, for Peter, we get, again, if you remember from before, we extract the Q-grams. That gives us a list of 4 Q-grams. We can now generate all the sublists, which only contains 3. So it's going to be hard after lunch, I know. If you have 4 Q-grams like this, we remove the first one. That gives us a subset of ET, TE, ER. If you remove the last one, then we have PE, ET, TE, which is this one here. And of course, if you remove the last Q-gram, then we get the same sublist here as if we get the one for Pete. So in a way, we generate all these variations, and that allows us then to basically put things into the same block. So in this approach, each of these sublists gives us a block. So all the records who have a certain sublist will go into the same block. So Peter will be put into 3 blocks or more. Peter will be put into 4, 5 blocks, etc. This works very well if data quality is bad. Computationally, it doesn't work at all. It completely explodes with regard to the number of blocks which we generate. A slight variation of this approach has also been developed about 10 years ago, which is called Canopy Clustering. So the idea is we build overlapping clusters. So cluster is a group of records which have some similarity. Canopy means they're overlapping, like you have umbrellas which overlap each other so it doesn't rain in between the umbrellas. Again, these techniques are based on set intersection, based on such Q-grams. The most simple thing you can imagine, every record which has PE somewhere in an attribute is being put into such a canopy. So PE becomes a canopy, ET becomes a canopy, TR, etc. So every record is put into many of these blocks, and then we generate these canopies, and then we generate blocks from these individual canopies. So that's there's software out there which you can download called Second String, which implements this, and that has been used in research. Quite a large number of papers are using this because it is freely available. Then another bit more esoteric, and there's many more different esoteric things. I just explained the last one. The idea here is that there's a lot of work on what's called multidimensional indexing. You're using this every day, but you don't know about this. Multidimensional indexing means we have data which is complex. In computer science, we map them into a high-dimensional space. The web, for example, every document becomes a point in a very high-dimensional space. And the idea is that we map our records into such a multidimensional space. So every record with certain characteristics becomes a point. And the mapping is done in such a way that records which are similar are being converted into points which are close to each other. So in a way, now we have let's say we have a 3-dimensional space, so we have a point here and a point here. They're close to each other. They're going to be put in the same block. A point here and a point there, they're different because maybe they have different names and addresses, so they're not going to be put into the same block. So these are techniques which are being, again, used in web search and in databases to provide fast access and things like that. They work very well. The challenges here are that mapping is a bit of a heuristic approach, so the dimensionality has to be selected somehow depending on the number of strings we have. And we're looking at something like 10, 20-dimensional spaces, if you could imagine that. So probably we can't, but these, again, research kind of techniques which in certain applications have shown to work very well, in others they haven't. Right, so one work we've just been doing recently, actually just going to be presented next month at the Data Mining Conference in Sydney. In many aspects of record linkage, we have to control block size. For example, in real-time linking, where we want to link, let's say, a query record with a database of records about people, we want to be able to control the block size, because the block size tells us how many comparisons we have to do. So this work comes out of a research project we have together with an Australian credit bureau. I don't know how it is in the UK here, but in Australia, if you apply for a credit card or a mobile phone or a house loan, everything like that, you go to a bank or to a bank, you provide identifying information such as your mobile phone number, your passport, your driver's license, electricity bills, etc. That information is being sent to the credit bureau, which matches that the identifying information with a credit database of people and their credit history. Because again, we don't have an identifier in Australia which we could use. I think it's very similar here in the UK. So the matching is with a query record, so somebody's personal details, the person who wants to get a loan, with that large database of 20, 30 million people. I'm assuming almost every Australian has a mobile phone or has a car or things like that. If you cannot control block size, if my name is John Smith and we use standard blocking, then my record will be compared to the 50,000 other John Smiths in Australia, which will take a long time, right? On the other hand, if I have a very rare name, then my record will only be compared to the 3 or 4 other people with a rare name. So we want to be able to control the size of the blocks. In privacy-preserving record linkage, which I talked about in the last hour, the size of block is also very important. We have to, because the block size reveals information about records. If I have a very rare name and I apply blocking in a privacy-preserving framework, then I get inserted into a very small block. That might mean that somebody who tries to identify information learns that this person here, or this record here, is in a block with only 3 people. That tells me something about the frequency of that name. On the other hand, if I'm in a block which is large, then it's potentially an attacker can identify this must be the block of the Smith, because they're very large, right? There's lots of records with that. So in privacy-preserving record linkage, you want to be able to control the size of the blocks as well, to put them into a very limited amount of min-max size. And the idea we came up with together with a PhD student is we do a blocking in an iterative way. We start by doing initial blocking, then we split large blocks and we merge small blocks, and we split and merge and split and merge and split and merge until we have all the blocks within a minimum maximum limit, which we can give as a parameter. So example here, we provide a set of ways of how we do the blocking. So for example, we start with first name, surname, and then I think postcode, etc. So here's our database, and you can't read what's over in the back, but let's assume it's just names. We do a blocking on the first name. So here we are, the John, the Jonathans, and the Joeys. Down here is Paul, and here is Peter. This block is too large. These 2 blocks are too small. So we merge them together because Paul and Peter have some similarity, of course. This block is too large. I forgot to say we want to have a maximum block size of 3 and a minimum block size of 2. This block is too large, so now we split on surname. So here's the John Smith and the Jonathan Smith. Here's the Joey Smith, and down here's the Joe Miller, and Joseph Milner's down here. So again, this is the right size. These are too small. These are too small. We merge them back together, and we do this merging and splitting and merging and splitting. And we get the blocks within that size which we need. And we actually can show that this improves the linkage quality later on quite a bit as well, which is a very good outcome. So this is just one example I'm very familiar with. There's other research, of course, happening in that area. But this is one of the first types of work which we looked at how we can control the size of blocks. And that's in an unsupervised way, so we don't need training data to learn something about block sizes. Okay, so let's move on to classification, which is probably the most challenging part of the whole record linkage process, as we talked about before the lunch break. So if you remember, in the traditional Philippian Santer, we calculate the similarities between pairs of records, we get these numerical values, we sum them into one single number. Then we classify, based on these numbers, matches, no matches, and potential matches. This is basically a classification, a binary classification problem. Well, the potential matches, with the potential matches, it's not a binary one, but we want to get rid of the potential matches. Right? Because the potential matches are the ones where somebody has to do the manual clerical review, which is time-consuming and expensive. And some poor person has to look at thousands and thousands of these record pairs and do the manual classification. So we want to come up with a binary classification, matches and non-matches only. So we want to get rid of the potential matches. So we call this a binary problem. We call it multidimensional. Because again, if we keep the vector of these similarity values, first name, last name, etc., it's multidimensional. Every attribute which we compare is a dimension. So this is basically a standard machine learning data mining classification problem. As input, we have feature vectors, which are our similarities between record pairs. The output is a binary classification. Are they the same person or not? So is it a match or non-match, right? So we can basically apply any existing machine learning technique on this problem. And again, almost everything has been used, from decision trees, support vector machines, regression, etc. Coming back again to the supervised, unsupervised case. Supervised cases means we need to have training data. So again, we need to know a subset of records which are about the same person. So we need to know these are the same people. And I had a discussion with somebody over the break, so the lunch break. Having only training data of people who are exactly the same doesn't help us. People who have two records which have exactly the same attribute values will give us a vector of just ones, right? If you have the same first name, the same last name, the same postcode, the same street address, each of these comparisons will give us 1, 1, 1, 1, 1, 1, 1. It's pretty obvious that these are the same person, right? What we need as training data is the really hard cases, the one where we have nicknames, the one where we have slightly different addresses and things like that. So training data has to be as diverse as the real data which you have in your database and what you would expect of people who are matching. And that becomes, again, as we discussed before, very domain dependent. The non-match status might be twins. So you have, if you compare two twins, they're going to have the same address, assuming they live with the same parents, same date of birth, the same surname, the same telephone number. The only thing which might be different is the first name. So the similarity vector for twins could be, it could even be Jonathan and John. I mean, people do these kind of things, right? So you might have a similarity which says 0.5 for Jonathan and John, 1, 1, 1, 1, 1, a non-match. Okay? Everybody would say, well, that's a match, that's the same person, right? And then we have the people who have changed their names, have changed their address. There's a typo in the date of birth, 0.5, it's a match, and things like that. Right? So we have, these are real cases, right? So training data has to reflect the variety of data which we have in a database and the similarities which we calculate. So I'm not going to go into the technical details of these classification techniques. These are really just standard machine learning data mining techniques. Off the shelf, there's R packages out there. There's Python, Java libraries which can do this. The art is not in applying these techniques. It's coming up with ways of describing the data and generating these feature vectors and coming up with training data. Because we don't have training data in many cases, recent work has looked into what we call active and semi-supervised learning. So the in-between fully supervised and completely unsupervised. Maybe I should talk about unsupervised first. So unsupervised means, again, we have no idea which compared record is a match and which is a non-match. So we have absolutely no idea about the truth. The only thing which we can do is we can cluster things. We can try to put all the records about the same person into the same cluster, to the same group of things. So again, we base that learning on the similarity calculations which we've done, but we don't have a true yes or no or match or no match outcome. So in between is active and semi-supervised learning. So here are techniques which if we have some training data, we can leverage this, maybe in a bootstrapping kind of approach, or we can use a human being to improve the classification as well. So in semi-supervised learning, we might have a few hundred true matches, and we can most probably generate several thousand non-matches from pairs which are completely different potentially. So this allows us to learn a first classifier, which will get it wrong maybe fairly commonly. But based on that, we can then do more. We can then learn better classifications on the weight vectors which we don't know the truth. So let's say if I learn an initial classifier, I apply that classifier on the whole data set. The classifier then tells me these record pairs are very likely going to be matches. These are very likely going to be non-matches. So the ones which are the clearest matches and non-matches, we can select for training data. So we actually increase our training data. Then we learn the next classifier, and we learn the next classifier, etc. Active learning is where we use a human being to help us classify difficult cases. Again, the 11111s and the 000s, they're normally easy to classify. It's the ones in the middle, right, which have some similarities and some differences. If we give these difficult cases to a human, a domain expert ideally, to classify, and that person then makes a decision that's a match, that's a no-match, that information flows back to learn the next classifier. So again, we do this in a bootstrapping approach. The more information we learn through active learning, the better the classifier gets. So the challenges, I think I mentioned this several times today already, we don't have training data. I mentioned the issue of the clerical review. So often there's the idea of, can we use information from the clerical review as training data? And I guess we can, but we have to be careful, right? Again, the clerical review traditionally is the record pairs which are not clear matches and not clear non-matches. So these are the very difficult cases. We have to be able to take into account that they're difficult, so the person who makes the manual decision might make mistakes as well. Unfortunately, most of these active learning techniques don't take the accuracy of the manual classification into account. And we've done a bit of recent work last year where we looked at that accuracy of the clerical review and found that as soon as it drops down, the overall classification becomes pretty bad. So it has to be, that's an issue. So how confident can we be that the clerical review is done 100% correct, which probably is not going to be right, because these are already the difficult cases. I mentioned this already several times. We don't have a gold standard in many applications. From a research perspective, for me as a computer science researcher trying to develop new techniques, I don't have access to real data, basically. Well, I do have to server collaborations, but unless other areas of computer science research, they have huge test data collections available. So there is information retrieval, web search, have test data collections. Machine learning has data collections which you can download data sets. In record linkage, we don't have that, right? So it's very difficult to do research in record linkage because we don't have real data. What we often do is generate synthetic data, and I'll talk about this a bit later on. I mentioned the collective techniques before, and I'll come back to them soon. So the idea here is that we look at the relationships between records. Right? So instead of deciding John Smith in one database and John Smith in the other database, that's a link, tick the box and move it away. We also look at the relationship John Smith has with other people. Is John Smith married to Mary Miller in both databases? Then it's more likely going to be the same John Smith, right? So show an example in a few slides. These techniques, they're highly accurate, but they're not that scalable at the moment. One problem if we do a simple pairwise linkage, so if we decide for every record pair individually that they are match or non-match, is that we might end into inconsistencies. It's called a transitive closure. So for example here, if I decide that record A1 is the same person as record A2, and record A2 is the same person as record A3, then by definition record A1 and A3 have to be the same person as well. It's a transitive closure. If these two are linked and these two are linked, then these also have to be a link. But if I've also linked A3 and A4 as being the same person, then A4 and A1 have to be, and A2 and A4 have to be the same person as well. And that's a problem. So for example, these two records might have a high similarity based on their name, and let's say date of birth. These two have a high similarity on date of birth and address, and these two have again a high similarity based on name and date of birth. So we have in fact two people who are somehow linked through a common address. What are we going to do? Well, we need a cut here, or we have to say all four records are the same person. And that problem occurs because we link individual pairs without looking at these grouping, these clusters, right? So there's a possibility that these chains can occur in certain applications, certain types of data, and that's a challenging thing to solve. Traditionally, this transitive closure has been dealt with as a post-processing step. So the pairwise Felici-Santo linkage has been done, and then another algorithm has looked at how do we now make the result consistent by either breaking links, like these ones here, or deciding everything is a link in a cluster, right? Every pair of records in a cluster is about the same person. The nice thing is with collective techniques, they do this by default. That's the whole design of these algorithms. Right, so what are these collective techniques I talked so much about? Here's an example. Now this is from the bibliographic domain, so papers and authors in a bibliographic database. And again, that comes back to the most research in that area is done in the bibliographic space because researchers don't get access to personal information. But also there's a case that in bibliographic data, we have a much richer environment. Let's say if I only look at customer addresses or patient addresses, or sorry, patient records, then I only have one type of entities, which is patients. There is not much relational information between different patients. In bibliographic data, I have this wonderful complex space of rich entities. I have papers. So we got P1 to P6 here. So these are papers written by co-authors. We have the authors. And we also have the place where they work, the affiliation. So we have three different types of entities: papers, authors, and affiliations. Sometimes we even have conferences and journals and things like that. So we can use these different types of entities and the different types of relations to find out in a much better way compared to pairwise linkage how we should link records together. So in this example here, which is about 10 years old by now, it's just a basic idea. There's again different variations and different techniques. So the problem we have here is we have two papers, P2 and P6, where we only know the initial of this D White. So we don't know if it's Dave or if it's Don. And that's highlighted in the figure here through the question mark and these dashed lines here, right? So also we have weight 1, weight 2, weight 3, and weight 4. So we want to find, in this very simple example, has Dave written paper 2 or has Don written paper 2? And has Dave written paper 6 or has Don written paper 6? That's kind of the linking of people to papers, right? So how do these classification techniques or these collective techniques work? The first step is to calculate similarities. What we've done the Felici and Santo approach, so basically pairwise record similarities. That gives us some numerical weight between paper and Dave, between some of these weights. But then we look at, maybe actually in this case it doesn't work. Oh no, we can. We can calculate Dave White, D White, Don White, D White. We can use a string similarity and that gives us a similar weight. Right? But again, there's not much we can learn. But now we're looking at the relationships, and that's basically the graph, the connections around these records. And if you imagine for a full database, it's going to be thousands and thousands of these ambiguous links, right? So the idea is that we do what's called a random walk in computer science. A random walk is some of you might know about this. We start in a place and we hop to the next using a connection. And then randomly choose one of the decisions we can make. We go, I mean, here the random walk is pretty straightforward. There's not many decisions we can take. But here we can now go down here, could go up here. If you imagine this in a large database, we have lots of different decisions which we can make. We basically count in this algorithm how many steps do I have to take to build a circle, assuming one of these two connections is correct. So if I assume that this is the correct, that Don has written paper 2, then I have to do 1, 2, 3, 4, 5, 6 steps to come back to paper 2. Because Don is connected through paper 1 with John, who works at MIT, where Susan works as well. If I do the same with the other decision, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to get to Dave. It's a much longer connection to get from paper 2 to Dave, because Dave doesn't have any direct collaborations with MIT. So in this case, it's much more likely that Don is the author of paper 2, because that circle is much, much smaller. So that's taking the relational information into account. And I mentioned before that these algorithms are computationally highly complex. As you can imagine, we have to basically do this for every ambiguous connection which we have. Once we've done that, then we find, so we have to calculate kind of a connection strength from paper 2 to Don, and the connection strength from paper 2 to Dave. If one is much higher than the other, we make the decision, yes, the co-author of Susan, that should actually be Susan, is Don. Once we've made that link here, then that link goes away. It doesn't solve this link over here, and there might be other ambiguities here. So each link which we make will trigger other decisions, potentially other links or links we have to cut, things like that. So we do this in an iterative way. And that's where the computational complexity comes in, right? The bigger the networks are, the bigger the number of these ambiguities are, the more we have to do calculation-wise. Okay, some sure questions of this afterwards. Right, so a bit more work which I've done together with my PhD students, which are specifically aimed at looking at census data. So that's where we have specific types of information. I think that might be of interest to some of you. So the first idea we had to look at households. So this is the idea of group linking or group matching. Again, we go away from the simple pairwise linkage, or actually rather we use the simple pairwise linkage as the initial step. So we link records across databases and households, and we build initial connections between individual people. So for example, here we have 3 households in 2 different censuses, one from 1851 and one from 1861. The arrows in between are the pairwise links which we build. And we can use this Felici-Santra approach I explained before to do this. The next question now is, can we use household information to actually identify which are the best households, or which are the households which are the same? Again, what we've done so far is we link households. We haven't looked at what happens if households are splitting or merging. That's then the next step in our work. There's different ways of how we can do this. The first thing is we just count how many people have we actually linked. So we've linked Henry with Henry, we linked Sarah with Sarah, we linked Henry with Henry the son, right? So that gives us 3 links here. We only have 1 link between Daniel and Daniel. So this is made up example, it's pretty clear that these 2 households should be linked, and these 2 households should be linked. Right? And then potentially these 2 households are maybe not, right? Because only 1 of 3 people is linked. Again, that linking, the group linking can be based on just counting the number of highly similar people, or we try to identify, get an overall similarity, or we can do this in an optimal way. And when we applied this on a small census data set from the UK, but we only had data from one town, about 20, or between 15 and 31,000 records, we were able to link many more households together compared to only linking individual people. And what's maybe more important is we were able to reduce the number of ambiguous links a lot. Right? So if you only look at individual people, you get all these possibilities that this household could be this and this and this and this. Once you take the household information into account, it becomes much clearer which households are actually linking together, which are about the same group of people. Right? So this work, student finished by now, she got her degree. Haven't found another student who continues working on this, but there's definitely a rich area of research looking at the temporal aspects here, right? Because obviously households are dynamically changing, right? The children move away. Children marry, start a new household and things like that. So taking the temporal information into account. That would be a nice research project for a PhD student. Another type of information which we try to take into account is things which shouldn't change over time. Again, looking at the temporal, the census records we had. This is what we call it's a graph-based approach. So we're basically generating a graph for every household. So again, we have two examples. This is the first household. We have three people. We have John, Mary, and Anton Smith. And over here we have Jack, Mary, and Tony Smith. We know that some of these things are changing over time. Age is changing, but age should change 10 years over a 10-year census period. So what shouldn't change are the relationships with regard to the age, right? So if I have children and my son is 20 years younger than me, then he should still be 20 years younger than me in 10 years' time. But we have data quality issues, right? So it seems in this census return, John didn't age as fast as Marie did. Right? So John only aged 7 years, Marie aged 9 years over a 10-year period. I guess that's just the data. People in those days didn't know the age, and it just, I don't know if they guessed the age, but these are pretty common things, right? What we can find out, or what we can extract from these households is, we know the age difference between John and Mary is 1. We know the age difference between the parents and their son is 31 and 30. In this record here, because of the data quality things, the age difference is -1, and the age difference between the parents and son has changed slightly as well. But they're not going to change completely, right? So what we're doing here is, once we have our households, for each of the households we build these small triangle graphs. If there's 4 people, we calculate the differences for the age differences for all 4 people. If there's 5 people, we calculate all the age differences. And that basically means that households now become more unique. It's not just the similarities between individual people and how many people in a household, it's also their characteristics, right? So there might be another household where the age difference between the 2 parents is 5 years here, or maybe 7 years here, but they have 2 children and the age difference are going to relatively be very similar. So we can use that to do a graph matching approach. So here we calculate not just the similarities between John Smith and Jack Smith and Mary and Marie and Anton and Tony, we're also calculating a graph similarity. Again, that gives us a value between 0 and 1. If the 2 graphs, so if these values here are exactly the same, so if they are exactly the same between these 2 graphs, we have a similarity of 1. If they're completely different, we get a similarity of 0. And then we combine the pairwise similarities and the graph similarities, and that gives us much, much better results. Right, so a bit more about generating synthetic data before we have discussion. I mentioned this a little bit before, that we have the challenge of getting real data as a researcher. So we can't simply download data about people and link them together. So somebody else before can be using encrypted data for record linkage research. No, we can't, because we need to have names and addresses for string comparisons, for the phonetic encoding and things like that. So we need real data. We don't get real data. So what we do? Well, we generate data. The idea here is that we have some partial real data, such as, for example, lists of typos and errors, maybe frequency tables of names and addresses, which potentially we can get from a telephone book. But we want to have data which is dirty. Right? So we basically generate our own dirty data. So the first step, the way we've developed several data generators. The way we've done it, we have these lookup tables of name and address frequencies. In the first step, we generate what we call the original records. Basically, randomly generate records with people's names, addresses, dates of birth. And then in the second step, we corrupt them. We introduce typographical errors. Because we generate the data, we can assign a unique identifier to every record. And that allows us then basically to link them back together. The good thing is, we know the truth, and we can publish the whole thing. So we have a data generator which is publicly available. We can also publish the data. And that has advantages and disadvantages. One of the disadvantages that we found when we published the first data generator and our software in 2003, we gave away very simple small data sets. And unfortunately, the number of people who use these really small, simple data sets for their research is scarily high. So instead of generating much more realistic data, everybody for at least a few years, they just took our 10,000 record simple data set and conducted their research on it. So that was a bit of a disappointment, actually. The question really is, how do we generate data which looks like real data, right? Having lookup tables with frequencies helps to generate more Smiths than Dijkstra's, and things like that. We can have rule sets and lookup tables to generate ages and all these kind of things. But introducing errors and variations is a very tricky thing. So I had an honor student a few years back, and he started by really analyzing what are the different ways of where data entry errors can happen. And we came with this really nice figure here. The source of information can be printed documents, handwritten documents, or it can be your brain. You can scan, at the moment, printed and handwritten documents. We haven't got an arrow through here yet. That's also not that far away, right? So at some stage, you'll be able to scan people's brain and extract information they have. I'm sure that introduces a new type of error. I'm not going to go there. We can dictate printed, handwritten, and you can basically say what your memories of your friend Johnny. Scanned optical character recognition data will introduce certain types of errors, such as variations of 1 and 7 might look the same, Q and G, so we have these similar looking characters. We can generate basically these types of errors. There are files out there on the web which basically tell us what are the most likely OCR errors. So Z and 2 and 5 and S and things like that. If somebody dictates things, or if you listen to somebody saying something, could be read from printed, handwritten, somebody can type it in. And so here we have typing errors, that you type the wrong key. I'm sure each of us has your own favorite typing error. I always type Sydney EN instead of NE. I don't know, my hand just do this every time. So everybody introduces their own typing error here, right? But again, we can model them. We can actually, now a data generator, we introduced a small function which basically tries to simulate left, right mistakes, upper, lower mistakes, depending on the keyboard. You can basically say, this is the type of keyboard, generate errors, typing errors. The phonetic thing here, the speech recognition, again, here we have the phonetic errors. And what we basically did is, if you remember back the phonetic encoding, soundex, double phone, etc., they are a set of rules which take a string and convert it into a phonetic representation of the string. So we basically re-engineered, we grab these rules onto the reverse thing. We extract phonetic variations from our strings, change those, and regenerate a different string. So we can actually generate Gale and Gale variations using our data generator. What else did I have? Typing as. So at the end of the day, we end up with an electronic document, the database of our names and addresses. So these are the ways of how we can generate pretty realistic looking synthetic data. And I'll show you on the next slide if I'm right. Yes, I'll show you some of the examples of that. That's an early version of our data generator. So the 3 blocks, the first one is typing error and abbreviation errors. The second one is phonetic errors, and the third one is OCR errors. What you also can see is we assign them unique identifiers. So we can say this is record 1, the original one. This is record 1, the first duplicate we generated. This is the second duplicate, and so on. So you can see there is 33. There's a missing value. We can do that. There is a strange typo here. Circuit is abbreviated in 2 different variations of circuit, as we found in Australian addresses. So that's based on a lookup table of known variations of circuit. If you look at the phonetic ones, I think they make sense, right? Desiree, Contreras, Barawang, beautiful Australian names. We have lots of those, and there's literally 100 different variations of Mooloolaba and Wollongong and all these kind of things. So it's a very nice, rich things to play around with. And the last one here, so this is an OCR error. The Y becomes a V, right? They're looking similar. How it becomes double V, and the G becomes a Q. So this is where the OCR got it wrong. I mean, again, where we generated the data based on such lookup tables. And if I'm right, yes, and this is the end of the third part. So I tried to give you a bit of an overview of what some of the research things which have been developed. We got plenty of time for questions.
Presumably you can then go on to use that generated data to test your methods.
That's the point of it, yeah.
But the trouble is that you generated that data according to the rules you know. What you should really do is get somebody else to generate data for you and then do an exchange, because these rules are presumably the things you would think of building into your own.
Yeah, no, I mean, again, as computer scientists, we want to develop new algorithms, and one aspect of it is, of course, testing. Yeah. Is the code actually correct? So the main purpose for us is to really testing, is the code correct? That's the first step. To overcome that issue is that if I generate the data, I know what I would expect. That's right. But the nice thing with this is I can generate 10,000 different data sets with different parameters of how many errors and what kind of errors and decide.
But you've still got the same rules in them.
But they're not exactly, again.
But would you use these rules when you're doing record linkage as well? Because you couldn't you? They're
not, I mean, again, what I mentioned is re-engineering the rules is a small aspect of this, right? Yeah. So the frequency distribution of names, for example, if I have more Smiths than Dijkstra's, I'll have to assume that because this comes from a telephone book which we have, this will be reflected in a contemporary database, right? I know there's disadvantages of this, but this is the only way of how many researchers in record linkage in computer science have to work, because we don't have real data. And even if we have real data, we don't know the truth, right? So we generate our own data. It solves some of the problems, it introduces other problems. I agree.
Yeah. Interesting. You've been too clear.
So this is actually, if you're interested, if you go to this website here, Gecko, this is actually an online demo, so you can, I hope it works. It did work yesterday. So you actually click on a web form and set in all the different parameters, and you can generate your own small little data sets. And you can also download the full code which sits behind that. Yeah.
Are there any good techniques if so rather than linking the data, my situation is I've received linked data, and I've got a whole bunch of stuff on one side that was given to me, and a whole bunch of stuff that's been collected. And I've got sort of one-to-one matching between everyone.
Right.
Just good ways to check. I guess what I'm interested in is weeding out things that probably aren't real matches. So good ways to sort of hypothesis-free comparisons between the two data sets to say, these ones are probably okay, but this one is like an outlier.
Right, that's a very good question, right? So if you have basic linked data and you don't know how it was linked and who did the linkage, and you can't talk to these people, or they don't tell you everything, can you kind of estimate how good the linkage is? I think that's probably more in the statistical area of doing estimates of linkage quality and things like that. I'm not aware of much research in computer science which has addressed that. In fact, there's a massive gap between, let's say, the record linkage community and the data mining community, in a way that I guess the same happens in practice, that certain people in an organization do the linkage, ship the linked data to the analysis people, and they assume, hey, it's linked, it's all 100% correct. So carrying that error estimates or the linkage estimates forward, that's an open research question, I think. But it's a very, very important thing to do, right? So I'm not aware of any specific work. I think Chris Dibben, he's been in contact with somebody, I can't remember his name, who was looking into these kind of, the statistician who's looking into these kind of things. But definitely a very important thing to consider and to solve in a way. Harvey Goldstein. Is that him? Yeah, Harvey Goldstein, I think, who works in this area.